Hello everyone, it's Natalie, and in this video I'm going to go over the Bohr model and how it can often come up in a general chemistry course. So the Bohr model is a depiction of an atom with the nucleus in the center and electron orbits going around it. One thing that's really important in the Bohr model is I'm going to show you an equation called the Balmer-Rydberg equation. And in this equation, there are two numbers that are integers, and every student I've tutored always identifies that these are integers, but doesn't always know the reason why they're integers. And why the two numbers, the n and m, in the Balmer-Rydberg equation are integers is because these values represent the orbit level that the electron is at. And the electron in this model cannot go between orbit levels. It's either at the n equals 1 level, n equals 2, n equals 3, and so forth. And the Bohr model, kind of the science behind it is a little bit complicated. I would be happy to make another video explaining the conversion from the electron with the emission of the photon. But for now, I'm just going to go into application. And so just writing out our basic equation, it's 1 over lambda for wavelength equals the Rydberg constant times 1 over m squared minus 1 over n squared. And in this equation, the Rydberg constant, that's in nanometers, and it's 0.01097 nanometers, and I misspoke, it's in nanometers inverted, so inverse nanometers, which makes sense because our wavelength will also be in nanometers. And then m, this is our lower energy orbit. And n is our higher energy orbit. And two other related points that often come up in solving these kinds of problems is converting between the wavelength and the frequency. So also always keep in mind that our conversion between wavelength and frequency just involves using the speed of light, because the speed of light is wavelength times frequency. And one other thing to keep in mind is this equation, that energy of the photon released is h, our Planck's constant, times f. And that value on Planck's constant is 6.626 times 10 to the negative 34 joules seconds. And joules seconds sounds like a really unusual unit until you think about how we'll use it in application. And joule seconds, those get multiplied by frequency, which is in inverted seconds or hertz. And so the seconds will cancel out. And you're left with our standard unit of energy, which is joules. So now going into some of the specific series, the one that comes up most often, or the two that come up most often, are going to be the Lyman series as well as the Balmer series. And sometimes questions can be a little bit confusing because the question doesn't tell you explicitly that m is going to equal 2, m is going to equal 1. It doesn't tell you the m value, but it tells you the series value. And so in the Lyman series, m, or our lower energy orbit, is always going to be equal to 1 because the electrons are going down to that m equals 1 orbital. In Balmer series, m is going to equal 2, and so forth. I most often see Lyman and Balmer come up, but of course, you'll have to see what they focus on in your own chemistry course. And so now we're ready to jump into these specific questions. So this first one says, use the Balmer equation to determine the frequency in hertz of the radiation corresponding with n equals 5. So let's write out the equation we'll be using. 1 over lambda equals our Rydberg constant times 1 over m squared minus 1 over n squared. And we are given that n equals 5. And this is the Balmer equation. We're using the Balmer series here. And so m is going to equal 2. And Rydberg constant is a constant, and we want to solve for frequency. So we can solve for wavelength using this equation, and then keep in mind, of course, that our frequency is just going to be that speed of light divided by our wavelength. And so let's first rearrange our equation to solve for wavelength. We know that we can do, or actually we're pretty well set for wavelength. The only thing that we need to change is that wavelength equals our Rydberg constant times 1 over m squared minus 1 over n squared. And this is raised to the negative 1 since it's inverted. And so our lambda is going to give us 0.01097 nanometers inverted, 1 over 5 squared, or 1 over 2 squared rather, 2 squared minus 1 over 5 squared. And this is all raised to the negative 1. And so when we solve this out, we get that lambda is going to be 434 nanometers. And so now we can plug this in, but make sure before solving for our frequency to convert to meters, because we use the speed of light, which is in meters per second. So it's going to be 2.998 meters per second, our C value, divided by lambda, which is 4.34 times 10 to the negative 7 meters. And so this is going to give us 6.91 times 10 to the 14 hertz, or seconds to the negative 1. And so just something to keep in mind at the end is our number of sig figs. Our number of sig figs is limited by the Rydberg constant because 2 and 5 are pure numbers. And so actually I could have kept one more sig fig. We technically have 4 sig figs here. So let's look at B, the wavelength in nanometers of a line in the Bohr series corresponding with n equals 7. And so B is pretty straightforward. All we need to do is plug in the n equals 7 to this equation for wavelength. So wavelength is the Rydberg constant times 1 over m squared minus 1 over n squared. And this is all raised to the negative 1. And so for this question, this is going to equal 0.01097 nanometers inverted. And this is times 1 over, again, we have that 2 squared because it's a Bohr series. And minus 1 over 7 squared, which is 49, close parenthesis, all raised to the negative 1. And this is going to give us a lambda value of 397 nanometers. And notice this wavelength is shorter than the wavelength that we got for part A. And this makes sense because higher energy has a shorter wavelength. And the Bohr series going from n equals 7 to n equals 2, that's going to require more energy than going from n equals 5 to n equals 2. All right, so we made it through all of that problem. Oh, so we still have a part C. So in part C, we see the value of n corresponding to a Bohr series line at 380 nanometers. So Bohr series, keep in mind m equals 2. Here we are given a frequency. And so, we're given a wavelength, silly, a wavelength. And so we can just plug that in and solve for n. So keeping in mind 1 over lambda equals our Rydberg constant times 1 over m squared minus 1 over n squared. And now we need to rearrange this equation to solve for n. So first we can divide over our Rydberg constant. So we have 1 over lambda times Rydberg constant. And then we can also subtract over 1 over m squared. This is going to equal 1 over n squared. And then I will multiply everything by a -1 to minimize our number of negatives. And so we have 1 over lambda, our Rydberg constant. And now this is going to be negative, and then our 1 over m squared is positive. So I just write it this way: 1 over m squared minus 1 over lambda times Rydberg constant equals 1 over n squared. And now we can raise everything to the -1/2 to get this in an n equals form. And so we'll be left with 1 over m squared minus 1 over lambda times our Rydberg constant raised to the -1/2 is going to be equal to n. And so now we can plug everything in. We have 1 over 2 squared minus 1 over, and we can leave 380 in nanometers since our Rydberg constant is in nanometers. That's the unit that we use in this equation. 380 nanometers times 0.01097 nanometers inverted. And this is all raised to a -1/2. And so this will give us 9.9, which we, of course, need to round up to 10 because we're looking for an integer value. And so in this Balmer series, n equals 10. All right, now for question 2, it says, what is the delta E for the transition of an electron from n equals 6 to n equals 3 in a hydrogen atom? What is the frequency of the spectral line produced? And so we'll actually solve for frequency first, because we can directly solve for wavelength, and then after that, convert that to frequency, and then use our Planck's constant to solve for energy. So let's start with keeping track. We have n equals 6, n equals 3. We're solving for wavelength. We know our Rydberg constant, and so we can use the equation that we've already rearranged just to get lambda directly. Lambda equals our Rydberg constant times 1 over m squared minus 1 over n squared. And this is inverted, so raised to the -1. Now we just need to plug in our numbers. Lambda equals, and we have 0.01097 nanometers inverted times 1 over, and now be careful because we've been working with the Balmer series, but in this one, we're no longer working with the Balmer series. Our m is going to be equal to 3. So we have 1 over 3 squared minus 1 over 6 squared, close parenthesis, and this is all raised to the -1. And so lambda here is going to equal 1093 nanometers. And so this is a longer wavelength than anything that we saw in the Balmer series. And this is appropriate because it takes less energy to go down to n equals 3 than it does to go down to n equals 2. And so this is an expected finding. And so now we can plug this in to nu, which is the symbol that we use for frequency, equals c over lambda. Again, c is our speed of light. So that's going to be 2.998 times 10 to the 8th meters per second. And this is going to be divided by our wavelength, which will convert to meters, 1.093 times 10 to the -6 meters. And this will give us 2.74 times 10 to the 14 hertz. So here we go. And again, we could have kept 4 sig figs here actually, because our limiting value is our Rydberg constant, and Rydberg constant has 4 significant figures. And so finally, we can go back to the first part of the question, which was solving for our energy. So the energy of a photon for the spectral line is going to be our Planck's constant times our nu. which is just 6.626 times 10 to the negative 34 joule seconds times 2.74 times 10 to the 14 hertz, or seconds inverted. And so this is going to give us 1.82 times 10 to the negative 19 joules. And if you think about the energy of the electron volt, this seems like an appropriate value for our energy. So we're done with question 2. And finally, I have one more question here. Calculate the wavelengths in nanometers of the first 4 lines of the Balmer series of the hydrogen spectrum, starting with the longest wavelength component. All right, so as we discussed, longest wavelength means lowest energy. So that's just going to be our series going from 3 to 2. And then we can add the next ones, 3 to 2, 4 to 2, 5 to 2, 6 to 2. And so we know our equation, just keeping that in mind for wavelength. It is our lambda equals our Rydberg constant times 1 over m squared minus 1 over n squared. And this is all raised to the negative 1. And so in going 3 to 2, we have 0.01097 nanometers inverted times 1 over our m squared, which is always going to be 4 here because 2 squared, minus 1 over n squared. 3 squared is 9, so 1/9. And this is all raised to the negative 1, which will give you 656 nanometers. Again, I rounded here more than is necessary. We could actually have 4 sig figs here. Next, going 4 to 2, we have 0.01097 inverted nanometers. So just nanometers to the negative 1 times, again, 1 over 2 squared, which is 4, minus now 1 over 16, 4 squared. And then this is all inverted. And so this will give us 486 nanometers. For 5 to 2, we have 0.01097 inverted nanometers times 1 over our 2 squared minus 1 over our 5 squared, 25. And keep in mind, of course, these 4, 25, 416, these don't have any units because they're pure numbers. These are just our orbital levels. And so that's why I've not been writing in any units for those numbers. 434 nanometers. And this is actually consistent with what we had gotten in question 1. So that's, of course, good. And finally, we have 0.01097 nanometers inverted times 1 over 4 minus 1 over 36. And raised to the negative 1. I forgot to put that in here. And this gives us 410 nanometers. All right, so hopefully this gave you a good idea of how the Balmer series and the Bohr model will often come up in application in a general chemistry course at the college level. If you have any questions, you can certainly comment, and I'll also have my private tutoring link in the description. I hope you found this helpful. Have a wonderful day. Bye.